All right, welcome everyone to Monday's class. This is for Monday, March 16th. This is the stuff that you would have normally gotten in class. You can see that in my top left-hand corner of the screen, it's actually Friday when I'm recording this, but things have been developing rather quickly here, as I'm sure you know. And we're getting quite a bit actually on our D2L page, and so I thought it'd be a good time for some quick administrative announcements before we get into the math for today. The first thing that I wanted to point out, so I'm going to go ahead up here and click on Content and jump in here. And I guess last off, I was at this Lab 5 section, and we'll talk about that here in just a second. But I want to go over here into the syllabus and course info. So right now we do have the old course syllabus up, and that's going to be changing, of course, with the exam 2 is for sure going to be like online or something, right? It's not going to be the in-person class exam that we had scheduled. So we still have to figure out some things about that, and so those will be some changes. But the big thing that I wanted to point out in this section is that we have here the instructor Zoom link in help hours. So I'm going to go ahead and click on this, and we can see with all of the instructors, no, I don't know why it's asking me to save a password, but okay. For all of the instructors here, we actually have, right, what hours they're available to help. So, right, we have these one set of course videos now that are taking place of the in-class time, and we're just recording them because, of course, the different time zones and all that sort of stuff can be a bit of a headache, or maybe if your internet's not the best at a given time, right, it may not be great. So just recording them, posting them, and then you can choose kind of the resolution and all that sort of stuff seems to make the most sense. But, right, that's not to say that we're not here to help you. And so all the instructors, right, they have hours in which they're available either on Piazza or via Zoom or things like this to talk with you guys and making sure that you're still keeping up with the material and learning the content. Likewise, so this was the instructor Zoom links and help hours. So I guess I'll do a shout out for my own, right? So my office hours now are going to be what used to be my class time, Monday, Wednesday, and Friday, 1:50 to 2:40 via Zoom, and there's my Zoom link right there. Of course, you can email me, but I prefer questions via Piazza, just so that way, hopefully the answers that I post can help everyone. Let me also jump back here and mention that we're in the process of collecting the TAs' office hours and Zoom links. So we have a few of them up here already, but your TAs will also be holding their office hours and whatnot via Zoom. The Math Learning Center is coming up with something like this, again, using Zoom. So there's going to be lots of opportunities for you to get help and stay up to date with the class. All right, so that's that. Let me jump back to content here. Of course, we have some of the links over here for the web work, online MLC, Piazza, all that sort of stuff. But I want to jump into the lecture content stuff. So this is the stuff for week 10, so 11.4 through 11.6. A lot of videos and whatnot. These ones are already done. But next up is going to be this week 11. So we're going to be talking about 11.8 through 11 and 11.9. Really, I'm interjecting here 11.7 as well. I think it's a very useful subject, and so that's why this video is going to be dedicated to that. But we can see here that we have a Lab 5 bin, so talking about some of these, and then also a bin for the video lessons. So, of course, we have some of these the notes that if you'd like to download and print these off, you certainly can, and some of the other kind of the standard videos, the pre-class videos, and then, of course, what I'm making here are the class videos. So, now, what everyone's been waiting for, right? Some information about the lab. So you should definitely spend maybe some more time than what I'm going to spend on this page here, succeeding at Lab 5. So again, as you saw from the supervisor's kind of initial long post here about what does the online course mean, all right, we're going to have individual responses for the labs, but otherwise they're going to be fairly similar to what we had before. So for instance, before you start the lab, you should still download the MATLAB code. You should watch the pre-lab video or read the pre-lab document, and you should complete the pre-lab assignment, right? So and similar to what we had before, though, it's going to be available on Monday and Tuesday. All right, then once you've done all these things, you're ready to begin Lab 5. So Lab 5 now is going to be through the D2L, it's called the quizzing feature. And this is where you're going to actually see the questions for Lab 5, where you're actually going to use the MATLAB code to come up with some answers, right? And you're going to submit them through this D2L submission thing now. As far as the grades go, well, you still have the pre-lab assignment, so that's going to be still 5 points, very similar to what it was before. As far as participation, well, now because you're doing an individual assignment, right, you're submitting it, right, pretty much everyone who submits a Lab 5 is going to get those participation points. So that's going to be great. Perfect 5s across the board. And then still 10 points is going to be based on your completion and accuracy of the lab problems. So that's how the split's going to be as far as the lab grading goes. And I can also show you, right, even though it's not active yet, the Lab 5, we can see here, let's see, that it's due March 18th at 11:30 p.m. So March 18th, that's going to be Wednesday night. Remember, all these times are Eastern Standard Time. So if you've changed the time zone, you have to adjust accordingly. But it's due Wednesday night, and it's open Tuesday early in the morning, right? 1 a.m. you could start this if you'd like to. And I can go ahead and click on Lab 5. Of course, it's not going to let me see the questions yet or jump into this, but you can see that you get unlimited time while it's open, although the estimated time required is going to be 50 minutes. Again, it reiterates all of the due dates and stuff like this. You get one attempt, and we haven't completed it yet. And so when this is actually open, you will see down here that there's just a little start button. And then that'll take you can read the questions then, and then using the MATLAB code, you can get the results and input them into D2L. And that's where we're going to get your submission and give you a grade. Okay, well, that is all of my administrative stuff for today. Let's go ahead and jump into the math. So I'm going to transition here now. There we go. I wanted to take some time and make a video about 11.7. So formally, there's no web homework about 11.7 or anything like this, but I think it's very useful. You know, similar to 7.5 for this, a huge chapter 7 about techniques of integration, right? I think it's good to have some kind of order of operations, right? What are some rules of thumb and how to decide, right? We have now a lot of tests. How do we know when to use the ratio test? How do we know when to use the integral test? How do we know when to use each one of these tests? And that in general is quite a difficult problem. And so I thought it'd be definitely a good idea to spend some time going over that sort of stuff here. All right, so let's go ahead and jump right into it and say what are some good techniques that I found typically that help us indicate how we should make progress in the problem. So the first one here, if the question wants to know what the series converges to, not just does it converge or not, but specifically, what does the series sum up to? Well, remember, we don't know at this point very many ways to do this. So right now, our only strategy is going to be the geometric series test. Now, every once in a while, you can do really clever things with something called like telescoping series. And later on, when we get Maclaurin and Taylor series and things like this, there'll be a few more other cases that we can, actually figure out what a series converges to. But right now, the only thing really that we can try, right, the only thing that we've really learned about is the geometric series test. And so it's very likely that if a question wants to know, right, if a series converges, what does it converge to? We should probably be using the geometric series test. Okay, on the other hand, moving forward, right, if the question has an exponential or a factorial, exponentials and factorials, these are some of the great things that the ratio test can take care of. So I think whenever possible, I like the ratio test quite a lot. I think a lot of students do as well. And so exponentials and factorials, that's a good indicator that the ratio test will actually give you a result, right? It was always really annoying when you got one out when you tried to use the ratio test, that it was inconclusive and you had to do something else. Well, sometimes those ones didn't have exponentials or factorials or things like this. And so that's probably why they weren't working. For number 3 here, if the question only has polynomials and roots, I recommend the limit comparison test. So the limit comparison test is a good one. So again, if you had some polynomials, but you also had an exponential, or if you also had a factorial, I would do ratio tests, right? This is kind of the order that I would be thinking about these in. But when you only have polynomials and roots, I think the limit comparison test is probably going to be pretty good. If the question has an alternating series, well, then the natural thing to try is going to be the alternating series test. And again, this is the order that I would go into, so that's assuming that, right, the ratio test got ruled out, right, that it didn't have exponentials or factorials or things like this. And so, okay, then I would go ahead and use the alternating series test, but still, I like the ratio test the best. So I would try that before the alternating series test. If you can look at it, you can see that, right, those terms, the a sub n's, as n goes off to infinity, that it doesn't look like they're going to 0. Well, that's a good case where you could use the nth term test for divergence. And then finally, the last bit that I want to give you is that if the question is in this form here, 1 over n times the natural log of n to some power p, I think this is one of the few cases that I've been able to find, right, that you have to use the integral test, that the limit comparison test doesn't work, that the ratio test doesn't work, that all of these things, they sadly don't work. Direct comparison tests don't work. When you have something like this, pretty much the integral test is the only thing that I've found that works for this style of problem. So that's kind of the last thing. I'd like to, I would prefer not to use the integral test if at all possible. All those hypotheses and everything, it's just not very friendly. But yeah, so I usually save that one for last. But I found that if it's in this form, sadly, you don't have a choice. You have to use the integral test. All right, so with that, that's really the only thing new for this section. Everything else is repeat, but hopefully we're now being able to solve these a little bit faster. So I'd like to apply the strategy now to a variety of examples. So example 2 does specify a test for us. Try to use the ratio test to determine if the following series converges or diverges. And if I was looking at the strategy here, right, I noticed that the strategy says the ratio test works well on exponentials and factorials, right? Well, sadly, I don't see any exponentials, right? I see polynomials. Here's a third degree polynomial on bottom. Here's a square root with a second degree polynomial inside of it, but I don't see any exponentials. I don't see anything, like 5 to the n. And I don't see anything with a factorial. I don't see anything like, n factorial, things like this. And so I don't have a lot of hope that the ratio test is going to work with this. Looking at this, I'd actually say that because we have polynomials and roots, really the limit comparison test is screaming out to me. But this one says, try to use the ratio test. And so, okay, fine, I'm going to try to use the ratio test. So let's go ahead and do it. The limit as n goes to infinity, the absolute value, I need my a sub n plus 1. So everywhere I see an n, I'm going to be putting n plus 1. So I'm going to have the square root n plus 1 quantity squared plus 1, again, all inside of my square root, divided by n plus 1 quantity cubed plus n plus 1 quantity squared. And then we need to divide that by a sub n. Well, I'm just going to multiply by the reciprocal. So multiplying by the reciprocal, we have n cubed plus n squared now on top, and root n squared plus 1 on bottom. Notice that all of these are positive terms, so these absolute values really are not doing anything. So let me go ahead. I'm going to drop these absolute values, and I'm going to combine kind of the like pieces. So all the stuff with the square roots here, and all of the polynomials, these third degree polynomials over here. And again, I've dropped the square roots because these are all positive things. Okay, well with this, right, since I've grouped together all of my square roots, and we just have this ratio of things with square roots, remember we can just do one big old square root here. And let me also maybe go ahead and factor this out, right? N plus 1 quantity squared. So that's going to be n squared plus 2n plus 1. And I can't forget I also have this other plus 1 over here. So I should include that as well. So I guess that maybe I could go ahead and combine these things, right? And I would get plus 2 altogether. And then in the denominator here, I have n squared plus 1. And I'm going to multiply that by, and notice that I have a cubic on top and a cubic on bottom, right? And if we looked at kind of their leading coefficients, right? So this is going to have 1n cubed, and I guess maybe I'm getting ahead of myself here, but this limit's going to be going to 1 over 1, right? Because again, kind of the leading coefficient inside of this, the cube bit, is going to be 1n, right? And so, okay, we're also going to have a 1 on bottom. So this is actually going to end up going to 1 over 1. And for this square root bit, right, remember you're allowed to push limits inside of square root. So again, you see this is just a quadratic polynomial on top, quadratic polynomial on bottom, and they have leading coefficients 1 over 1. And so this is just going to be the square root of 1 over 1 times 1. And that's what the limit's going to be. Again, we're using a lot of our kind of algebraic techniques, a little bit of our calculus 1 here in order to solve these limit problems. And so with this, we get 1. And so just like I was saying, this is a good indicator, right? Our strategy seems to be telling us, well, accurately at least, that the ratio test is inconclusive. So sometimes I've seen, as previous exams and things like this, maybe this would be like a multiple choice style question, right? So a multiple choice style question that I've seen on maybe a previous exam, right? It would be, part A or option A would be that the ratio test says that it converges. Option B would be the ratio test says that it diverges. Option C could be that the ratio test is inconclusive, but it actually converges because of something else. And option D could be, the ratio test is inconclusive, but it actually diverges because of something else. And E could be none of the above. So this actually could be a fine, multiple choice style question right here. All right, so with that, we can see that their strategy seems to be working. Let's go ahead and try another problem here. Asked to determine if the following series converges or diverges. Now, I see on top we have a polynomial, something like n cubed plus 1, and in the bottom we have an exponential. We have 5 to the n. And so, okay, there's a little bit of conflict here, right? Because we know that the ratio test is good at exponentials and factorials, and we know that the limit comparison test is good at polynomials, so things like this n cubed plus 1. So we need to decide, right, which one should we use? And so you have to be careful with this wording, right? So if the question has an exponential or factorial, try the ratio test. So yes, it has an exponential in this case, so that would be a good thing to try. Notice that this one says if it only has polynomials or roots here, then we could go ahead and try the limit comparison test. So in this case, everything seems to be pointing towards 2. We should try the ratio test in this case. So let's go ahead, give the ratio test a try. And hopefully we can actually get a good result this time. So the limit as n goes to infinity, the absolute value of n plus 1 cubed plus 1 over 5 to the n plus 1 power. And then we need to divide by a sub n, or I'm just going to multiply by the reciprocal here. So 5 to the n divided by n cubed plus 1, all inside of our absolute values. Again, as n goes off to infinity, all of this stuff is positive. So these absolute values really are not necessary here. If we had an alternating series or something like this, absolutely, we would need them. But when everything's positive, you can pretty much drop these absolute values darn near right away. All right, so now let's go ahead and combine all of the like pieces. So all of the polynomial stuff, all of the exponential stuff, and hopefully some stuff cancels, right? For these exponentials, notice that we have n5s on top, and we have one more on bottom. So imagine, right, if we had something like, that's probably a bad number to choose, maybe not 5, but maybe if we had like 7 on top and we had 8 on bottom, right? There would be a lot of cancellation, and we'd be left with just one more 5 on bottom. So all of them on top cancel, and almost all of them cancel on bottom. There's just one 5 left on bottom. And so we're left with, right now, the limit as n goes to infinity, and here we're going to have 1 over 5. Now for this polynomial stuff, right, we can see maybe looking at this that these are both cubic polynomials and their leading coefficients are 1 on top and bottom. So last time I just said, okay, so it's going to be 1 over 1. If you really wanted to show more work for this, right, the thing would be is to FOIL this all the way out. And you have to remember, right, it's very tempting, but I've seen people get marked down for this, right, that this is not equal to n cubed plus 1. Remember, you have to actually FOIL it all out. So it's n plus 1 times n plus 1 times n plus 1. That's literally what it means to be n plus 1 quantity cubed. And so maybe we could go ahead and FOIL out the first little bit here. So that would be n squared plus 2n plus 1. And then we need to multiply it by n plus 1. And so let's see, if I multiplied the n piece by all of these things here, what I'd have n cubed plus 2n squared plus 1n, and then when I multiplied the 1 by all of these pieces, so if I was to go ahead, the second bit, the 1 by all of these, right, I'd have plus n squared plus 2n plus 1, and so I'd have n cubed plus 3n squared plus 3n plus 1. And by the way, there is a faster way if you happen to remember Pascal's triangle, this whole 1, 3, 3, 1 sort of deal. You could also get to this a bit faster. But again, the big thing here is that your leading coefficient is 1 n cubed. And again, you have 1 n cubed in the bottom. And so when you take that ratio here, let's go ahead and write this all out. N cubed plus 3n squared plus 3n plus 2, right? We need to include this extra 1 up here. And then on the bottom, we have n cubed plus 1, that these things both have leading coefficient 1. And so the limit as n goes to infinity, we're going to have 1 over 1 times 1/5, and that's going to be 1/5 altogether. That's indeed less than 1, and so hooray, the ratio test works. And the ratio test says that this is absolutely convergent. Notice our choices were just convergent or divergent, and so yes, the ratio test will conclude that this converges. So I'll say converges by the ratio test. All right, so that's kind of, again, employing our strategy here in order to figure out what should we do when we get kind of a random problem like this. All right, let's go ahead and move on. And I would like you to maybe pause the video, try this one on your own. Try to go through the strategy and figure out what would you do for a problem like this. Okay, so again, pause the video, give it a go, and then when you're ready to spoil the surprise, go ahead and unpause it. All right, so here is my work for our fourth example. Notice I went back to the strategy, right? So the first thing that I asked myself is this a geometric series test? Well, in this case, right, it wasn't asking for us, what does it converge to, for instance. So it wasn't very, I wasn't thinking the geometric series test anyway. But look at this, right? This isn't even a geometric series. So sadly, we couldn't use the geometric series test even if we wanted to. Moving on to the ratio test. Well, I don't see any exponentials. I don't see any factorials. So this one is also out. Now, the limit comparison test is a bit tempting. The limit comparison test, we could try to give this a go. I do see a lot of polynomials. Unfortunately, they're all inside of a natural log. And remember, the limit comparison test doesn't do so well with natural logs. And so if you try to compare it, there's a way that, you don't necessarily dead end or anything like this. It just takes you a little bit longer, and eventually you get to the same spot. And that's going to be step 5, is that in order to show this, we're going to need to use the nth term test for divergence. But, kind of going down the list, 4 was alternating series test. No, it's not alternating, so that one's kind of out. So yes, 5. Do we have any hope that if you were to just look at the items on the list, right, the sequence itself, and let n go to infinity, right, does that equal 0 or not? And so we ask, well, it's a little hard to say. Let's go ahead and dig into things a little bit. The first step that I'd like to do is I'd like to push this limit inside of the natural log. Remember, you're allowed to do this because the natural log is a continuous function. And whenever you have a continuous function, you're allowed to push limits inside. So I went ahead and I pushed the limit inside of my natural log. And now I just have to worry about, right now, the limit as n goes to infinity of 7n divided by n plus 1. Well, this is a polynomial over a polynomial, right? A rational function. And so we can go ahead and use L'Hopital's rule or some Calc 1 stuff, or just, again, we could look at the ratio of these leading coefficients, right? Because these polynomials have equal degree. And so in this case, it'll be 7 over 1. Well, that's the same thing as 7, and the natural log of 7 is not 0. And so, by the nth term test, we know that our series here, summing up the natural log of 7n divided by n plus 1, what was it, from n equals 1 to infinity, diverges. Remember, the nth term test for divergence says if that's anything but 0, even if it does not exist, right, it's going to diverge. It's only when it's equal to 0 that the nth term test for divergence says, I don't know. Right? Maybe it diverges, maybe it converges, I just don't know. But in this case, because it's not 0, we know for sure that it diverges. All right, so again, that's how I would use kind of the strategy in order to solve a problem like this. All right, let's go ahead and move on here. Determine if the following series converges absolutely, converges conditionally, or diverges. So I have it written like this. Let me go ahead and maybe do a quick rewrite here. sometimes, right, whenever I see these things with the negative exponentials, I like to rewrite them and see them for what they really are, right? So this n to the negative 1/3, well, that would be n to the 1/3 in the bottom, or that would be also the same thing as just the cube root of n in the bottom. So that's really what this thing is asking about. Okay, and so again, we need to kind of go down our list here. So this isn't a geometric series, so you can't use the geometric series test. So kind of 1 is out. For 2, the ratio test. Well, I'm kind of tempted for the ratio test, but unfortunately the ratio test cannot be used. Let me finish writing this out. There we go. So the ratio test also cannot be used, but why I'm tempted is because this right here looks like an exponential. But the problem is it's not really an exponential. Even though our variable, our n, is in the exponent slot, right? This is just an alternating piece, right? It doesn't actually, if you were to draw a bunch of exponentials, things that look like this or things that look like this, right? That negative 1 to the n plus 1 isn't really an exponential curve. And so in fact, when you try the ratio test on this, you can try it, right? If you can't see it, I recommend that you definitely try it out. You're going to get that the limit equals 1, and so that it's inconclusive. So sadly, right, this really isn't an exponential. That negative 1 raised to the n plus 1 isn't a true exponential here. So now moving on, right, maybe step 3, I would say, well, maybe the limit comparison test. Well, remember the limit comparison test, that's fine for positive series, but kind of the fact that we have this alternating piece, right, that's a little bit worrisome. However, look at this. We're asking, right, does it converge absolutely? So maybe, right, if I was interested, does it converge absolutely, I would like to try to figure out something about the absolute value of negative 1 to the n plus 1 divided by the cube root of n, right, to test whether it converges absolutely. So for this, maybe the limit comparison test really works, right, because when I apply this absolute value, we're going to get 1, and then on the bottom we have the cube root of n. Right? So again, the cube root's already positive as n starts at 1 and goes off to infinity. And the alternating piece, whether it's negative 1 or 1, either way, when you take the absolute value, you just get 1. And so this right here, well, we can see that we do have just polynomials. On the top, it's a really boring polynomial, a constant polynomial, and roots. And so this is exactly when maybe the limit comparison test shines. So let's go ahead and try the limit comparison test for this. Well, the limit comparison test, you would say, well, wait. Do I really need the limit comparison test? This is already fairly simple, right? This already looks like 1 over n to some power, 1/3. And so in this case, we don't even need the full strength of the limit comparison test. This one's actually nice enough that we can just look at it and say that it diverges by p series. Oops, p series. So this diverges by p series so that there's no way that it's absolutely convergent. So maybe it converges conditionally, or maybe it just actually diverges. But from this right here, we can say that it certainly does not converge absolutely. All right, so let's go back to the original problem now. The original problem, again, with this negative 1 raised to the n plus first power divided by the cube root of n. And I'm assuming that, you've probably been screaming it at the computer screen here, right? This is an alternating series. And so it makes a lot of sense, right? If you want to know, does this series itself converge or diverge, you should probably at some point be thinking about the alternating series test. So the alternating series test, let's go ahead and give that a go. The alternating series test, in that case, you would probably rewrite it something like this, right? You kind of want to break up and you want to have the alternating piece, and then you want to have these b sub n's, right? This positive piece. And remember, the alternating series test had 2 things that it needed. So first of all, it needed that the b sub n's are decreasing. And that's true because, right, in this case, the cube root of n is increasing. And so its reciprocal, 1 over the cube root of n, is decreasing. So it is indeed decreasing. That's great. And the second thing that we needed is that the limit of those b sub n's, the positive pieces, that this should go to 0. And well, yes, kind of as n goes off to infinity, right, the cube root of very, very large numbers does get very, very large. And so you get something like 1 divided by infinity. Well, that's not exactly proper math right there, but 1 divided by a very, very large number is indeed 0. And so the 2 hypotheses for the alternating series test are met. And so, by the alternating series test, it converges. By the alternating series test, our original series converges. All right, so we have the original series converges, but when you take the absolute value of it, right, this does not converge. And so these two together make up what we know as conditionally convergent. So I'm going to say, so the series converges conditionally. All right, and that is the answer to example 5. All right, one more to go. Again, please go ahead, pause the video, try this one on your own, and then we're going to come together and talk about the solution. So again, pause the video, try it on your own. All right, so here's what I have so far. I went down the list, right? Number 1, is it a geometric series test? Well, it's not asking what it converges to, so probably not in this case. And looking at it, right, it's not a geometric series, so okay, we can't use the geometric series test. Ratio test, well, I don't see any exponentials, I don't see any factorials, so my hope's kind of gone for that. Limit comparison test, again, not so much. That natural log kind of ruins things, and it already looks pretty simple. Sadly, none of the comparison tests will work on this. Alternating series test, well, it's not an alternating series, so that's out. The nth term test for divergence, well, if you try it, you get that the limit is 0, so sadly, it doesn't know. And so we're at 6, right? The final thing that I told you guys to try is if you have a sum that looks like 1 over n times the natural log of n to some power, then in that case, this is one of the few cases where the integral test is necessary. So even without saying the integral test, this is one that just the integral test is the only thing that works for it. And so, okay, we need to use the integral test. Remember the integral test, this was kind of maybe the most painful one. It had all of these hypotheses. You had to say something about being at positive. You had to say something about why it was decreasing. And you had to say something about why it was continuous. So all of these things. Well, okay, so let's go by these one at a time. Remember that n is greater than or equal to 2. So we're starting off here at n equals 2 according to our series statement. And so kind of all of these pieces are positive. So I'm going to say, so 5 is greater than 0. That one's kind of silly. But n is greater than 0, right? It's 2 or bigger. And also, we have that the natural log of n is going to be greater than 0, right? As soon as you get bigger than 1, that's the case. And so all of these things are positive. And so when you go ahead and you take ratios and you multiply together a bunch of positives, right, it's positive. So 5 divided by n times the square root of the natural log of n, right? All of these things are positive. I guess also you have to mention that, right, the square root only outputs positive numbers, right? So this altogether is positive. So this is my one sentence phrase that I would kind of indicate why this is positive. For decreasing, I would say, well, that n and the square root of the natural log of n are increasing functions. So when you go ahead and you multiply them together, they stay increasing. Oops, that should be a square root of the natural log of n. And when you take the reciprocal of those, and you can multiply by any positive constant here, so 5 isn't a problem, this becomes decreasing. So again, you should remember that the reciprocal of an increasing function is decreasing. So this is my one sentence to go ahead and show that this is a decreasing function. And then finally, continuous. Well, in order to show that it's continuous, usually we say where the discontinuities are. So I'm going to say here the function is discontinuous at n equals 0, right? So again, kind of the places that you'd have discontinuities are when you're dividing by 0. So if n is equal to 0, that would be bad. I'd be dividing by 0 there. And let's see, if this was 1, right? The natural log of 1 would be 0, and I'd be dividing by 0 there. So it's discontinuous at n equals 0 and n equals 1. But notice as soon as you hit 2 and beyond, right, smooth sailing. So f is continuous on the interval from 2 to infinity. So 2 and beyond. Or really, if you want to be a little bit more proper, right, maybe you should say these a sub n's are continuous and everything. But okay, this is fine, right? And so, okay, those are what we need in order to link it together with some improper integral. So whatever this improper integral does, the integral from 2 to infinity of 5 divided by x times the root of natural log of x dx, whatever this improper integral does, our series is going to do the same thing. So if the improper integral converges, our series will converge. If the improper integral diverges, our series will diverge. And so now we've switched out our chapter 11 style problem for a chapter 7 style problem, right? We need to figure out how do we integrate this thing and evaluate it. And so we need to go back to our chapter 7 days, and we have to think for a little bit, right? How would I go about integrating this? And if we were to go down our strategy for integrations in chapter 7, really the first thing that we ought to try is a u substitution. So for our u substitution, I think usually u being an inside function makes a lot of sense. So I think u is equal to the natural log of x. Notice the natural log is inside of the square root function. That seems like a reasonable thing to try. Du would be equal to 1 over x dx, right, if I was to take the derivative on both sides. And if you'd like to, you could go ahead and rearrange this and write x times du is equal to dx. So now let's go ahead and start substituting some things in here. And let's see. So 5 x, we're going to have root u, right? U is the natural log of x. And instead of dx, I'm going to write x times du. And again, remember what you're looking for a u substitution to be successful, you need to completely transfer over all of your x's to u's, right? You're only allowed to have a single variable here. So now our single variable that we're using is u's. If ever you're kind of halfway in between, you have some x's, some u's, then that's an indication, right, that maybe u substitution is not working out for us, and we need to rethink about things and maybe try integration by parts or something else, right? All right, so with this, well, this we can integrate. This is a lot simpler actually, right? Remember that this is just the same thing as u to the negative 1/2 power. So if I wanted to integrate this, well, according to our rules, right, I would need to increase my power by 1. So I'd go from u to the negative 1/2 to u to the positive 1/2. And then I'd multiply by my reciprocal. So reciprocal of my new exponent here, so 1/2, the reciprocal of that is 2. Let's not forget, right, we have a 5 kind of tagging along here. That's just a constant, so that's along for the ride. And so we're going to have 10, and this is the square root, and instead of u, I'm going to write the natural log of x. So the natural log of x. And now remember, we have to evaluate this from 2 off to infinity. Or if you want to be a little bit more proper about all this, right, this would be 2 until t. And t needs to go off to infinity. So we could go ahead and plug some things in here. So let's see, I'd have 10 root natural log of t minus 10 root natural log of 2. Oops, and I forgot my limit. That's very important. I want to make sure to include that. The limit as t goes off to infinity. And the big thing here, right, as t goes off to infinity, the natural log of very large numbers is also very large. And when you take the square root of a very large number, that's also very large. And so you're going to have infinity minus who cares, right? This is 10 root natural log. It barely matters, right? You have a very, very, very large number, and you're subtracting away a little bit, right? And so this is going to be infinite, that it diverges. And again, remember that the integral test says that the series and the integral share the same fate. So because this improper integral diverges, we know that our series is also going to diverge. So I need some conclusion statement to say that, why do we care about this here? Why does the series care about it? And so I'm going to say, so since the improper integral diverges by the integral test, our series that we were interested in solving for diverges. Our series diverges. And that's how I would finish up this problem here. Sorry, I was running out of some room here, so I had to kind of squish it in. again, the integral test, that usually takes a bit of time and everything, as you see here. And so that's why we usually save that one for last, right? If at all possible, I'd like something else to work out, but sometimes it doesn't. None of the other tests work, and so sometimes you have to use the integral test. All right, I hope you guys enjoyed this video. I think that's probably a good place to end there. Again, the big thing about this video is trying to decide when we should use each one of these strategies, and I think that this is a decent outline for when to use what. So, all right, if you have any questions or if things are still unclear, again, please post on Piazza. I'd be happy to help you guys, or come to your instructor's office hours. I had some office hours today, technically. I didn't advertise them nearly good enough, but yeah, no one showed up. And so, yes, we're definitely here to help still, so please come on by, ask questions if anything's unclear. All right, I'll see you guys next time.